Hi everyone, I'm Vikrant Kumar, a PhD student in electrical engineering at Columbia.
I'm Oliver Durnan. I'm also a PhD student in electrical engineering.
Hi, I'm Rojan Banmali. I'm a computer engineering student here at Columbia University.
Welcome to the video demo for class 6350 VLSI Design Lab.
So this is our project. It's a digital display driver made for a custom-built 20 by 20 micro LED display that's fabricated here at Columbia.
In this video, we're going to show you a quick demo of what our chip can do. I hope you guys enjoy it.
First, to show the operation of our chip, we'll demonstrate a few preloaded programs. The first one shows that each pixel on the display can be individually illuminated by scrolling through them one at a time. This program is primarily used for debugging connections to the test display. Next, we've programmed a block bouncing, which is reminiscent of some old TV screensavers. This program shows that the chip can display a smooth video without screen tearing. Third, we've included a program for displaying various pixel art images for demonstration purposes. Each image displayed is sent to the display driver in the form of a series of 20 instructions, each 32 bits long.
This is our evaluation board. It is powered by a 3.7 volts lithium-ion battery. There are two LDO regulators on the board that steps down 3.7 volts from the battery to 2.5 volts and 3.3 volts. 3.3 volt supply powers the microcontroller. 2.5 volts powers our chip. The microcontroller we have used is an ARM Cortex M0 microcontroller. The microcontroller supplies 5 signals to our chip: clock, clock 2, reset, data, and data latch. These 3.3 volt signals are first converted to 2.5 volt signals by logic shifter before driving our chip's 2.5 volts inputs. In addition, there are two settings on the board. One disables the PWM. The other selects clock 2 as the clock source for scanning. Clock 2 is optional and intended for debugging purposes only. Here, our chip is shown on the top of the board. When the board first boots up, the program on the microcontroller starts the clock at 1 MHz. Then the reset is asserted for a few clock cycles. After that, based on the demo selected, using 4 keys on the board, the microcontroller starts to send data to our chip. Note, we have used standard SPI bus protocol to transfer data, and the SPI clock is the only clock used by our chip.
To explain how the chip works, we will use the block diagram. The SDI, SLAT, and SCLK signals flow into the addressing logic. These signals contain the clock signal, instruction data, and instruction timing information. The instruction data contains a row address, column data, and a brightness level. The addressing logic then interprets the instruction and writes the data into the chosen row of the memory as shown by the orange signal. At the same time, the brightness level data is sent to the PWM generator block and is used to set the duty cycle. Completely asynchronously, the scanline generator is creating enable signals for each row of the display. Due to the passive matrix design of the display itself, the rows must be enabled one at a time. Simultaneously, the scan generator is sending read signals to the memory so that when a row is enabled, the data which should be shown on that row can be retrieved. These signals are sent to the row and column drivers, which are large devices used to supply sufficient current to the display. The PWM enable signal is used to set the state of a multiplexer, which either allows the PWM block to be bypassed or uses the duty cycle generated by the PWM block to set the duty cycle of the voltages asserted by the drivers. Finally, at the top of the block diagram, there is a power on and reset circuit, which is used to initialize the PWM and scanline generator blocks when the chip is first switched on. Importantly, the memory read and write operations are completely agnostic to each other, so the write and read halves of the circuit do not need to be synchronized and can even operate on separate clocks if desired. The main outputs of the chip are shown on the right side and will be the 20 row drive pins and the 20 column drive pins. The next image shows the top-level schematic of the chip. Roughly, the red area is the addressing logic, the white area is the memory, the scan and PWM generation are in yellow, and the row and column drivers are in the green square. To ensure sufficient power to turn on the LEDs on the display, and to avoid using logic level shifters on the chip, every block in this chip uses the 2.5 volt high voltage devices that were available in the chosen technology node. All blocks were also designed and laid out by hand, because synthesis tools were not available for the 2.5 volt devices. Now, we'll move on to discussing the physical layout of the design. This image shows the full chip as seen in the layout editor. The active area of the chip sits in the center, covered by power grids used for distributing VDD and ground signals around the chip. The large traces extending from the center toward the pads on the periphery are the high current output pins for the drivers, as well as the VDD and ground pins. The smaller traces, primarily on the left side, are the input signals for the chip. Looking a little closer and removing the power grids, we can see the floor plan more clearly. From this picture, we can see that most of the active area on the chip is used by the driver transistors which power the display, the memory, since it contains 400 individual memory cells, and the decoupling capacitors. Zooming in even farther, we can see how the physical blocks on the chip are laid out in such a way as to minimize the number of interconnects required. At the same time, blocks that are on the same path are all designed with the same bit pitch, allowing them to be easily snapped together. In the remaining part of the video, we will show some testing to further demonstrate what the chip is capable of and how it works. The first clip shows the row scanning behavior of the chip. As explained previously, the passive matrix design allows for one row of the display to be illuminated at a time in order to reduce the number of I/O pins required. Usually, the display is clocked at a high enough rate such that it appears to show a constant image, even though only one row of the display is actually illuminated at any given time. As the clock rate is decreased, the image starts to shimmer, and eventually the scanning is slow enough that the camera filming it can begin to pick up groups of rows and then individual rows lighting up. Further decreasing the clock frequency makes this effect even more apparent. Finally, we can see how the chip is scanning through the display, enabling only one row at a time. In the next clip, we vary the clock rate from 100 Hz to 10 MHz, increasing by a factor of 10 each time. The image starts to look consistent between 10 kHz and 100 kHz. After that, we tested the high frequency limits of the chip. To do this, we borrowed a high frequency signal generator to use as our clock, capable of generating gigahertz square waves. Unfortunately, our display was not able to go that fast. In this video, the clock speed is constantly being increased in steps of 1 MHz, and we see that when the display fails, the clock frequency is 165 MHz. This indicates that the maximum clock speed in this setup is approximately 164 MHz, which corresponds to a refresh rate of 512 kHz on the display. Another functionality of the chip is pulse width modulation for brightness control. Here on the oscilloscope, the yellow trace on top shows the PWM signal, and the green trace on the bottom shows the signal sent to enable a single row. Observe that the pulse duty cycle can be decreased or increased in steps of 1 microsecond at a time. Now, looking at the chip on the PCB, we can observe how the brightness level is controlled by the push buttons, and that decreasing the duty cycle reduces the perceived brightness of the image. After showing that, we can return the display to its full brightness level.
The current display serves as a prototype for demonstration purposes. Our chip will eventually be used to drive a 20 by 20 micro display with an individual emitter size of 20 micron. One such micro LED under test on a probe station is shown on the right. The micro LED will be mounted on a carrier PCB shown on the left to connect it to the main PCB board. Finally, the microLEDs will be used for the selective optogenetic stimulation of neuron cells in a mice in a miniaturized setup. The illumination patterns generated on the microLED display and controlled by the driver IC will also be used as a light source for implementing various computational imaging techniques such as structured illumination microscopy and snapshot compressive imaging. Thanks for watching.